A very good morning to everyone and welcome to 15th day of Deep Learning Summer School by Triple ITDM Jabalpur. I am Sunana Singh and it is my pleasure to chair this session. I hope you all are enjoying the session so far and practicing along with the sessions. We are delighted to welcome our next speaker, Dr. Madan Dabiru, the founder of Aizen, a startup working at the forefront of autonomous AI systems for video data. With over 18 years of experience in AI, ML, and data science, he leads the development of an AI generating algorithm that can evolve and learn on its own. His work spans computer vision, NLP, customer sciences, and even cancer research, and he holds multiple patents and publications in these areas. I welcome you, sir, and request you to kindly take over the session.
Yeah, thank you so much. Can this be an interactive session or is it just I have to talk about it?
Sir, it's on you. It can be an interactive session. I will unmute participants.
Oh, nice. Okay, okay. So just wanted to know that how many of you just have fair understanding on this reinforcement learning and how many of I'm talking on mute. Okay. Okay, how many of you are having the fair understanding on this reinforcement learning so far? Okay, you may answer it here in the messages I can see. Can you just type your messages? Yes or no, kind of, please, so that I will have a fair understanding where exactly we are. No, no. Okay. No. Okay. No. Okay. No. Okay. I haven't seen any S yet. That's fine. I think I have received a fair amount of them. Okay. Let me share my screen and walk you through some of the interesting aspects of it. Then we'll deep dive into it. Okay. Yeah, great. So let me share my screen and I have a presentation here that I would like to cover. I would like to just to take some time in explaining what exactly the intelligence part of it. Then we can actually deep dive into what is the reinforcement learning and everything. Okay. And please type your message so that I can actually have some understanding about, okay, what exactly you are asking. Please feel free to ask questions and everything. Okay. All right. So yeah, my name is Madan. I had done my PhD from IIT Kanpur and then postdoc from Maryland Robotics Center, University of Maryland College Park. So where we had actually implemented many of these reinforcement learning algorithms for unmanned vehicles. So before we actually get into this reinforcement learning, I would like to give a very fair understanding of what exactly the learning part of it. Okay. So, we have actually started with the uh, kind of stone age to calculator age. Today we are like chat GPT age, right? So any kind of question comes, people go to chat GPT and ask, hey, what is happening? What about this particular question and answers? But have you ever thought that how this system has been implemented? Okay. So there are two ways generally. Okay. I'll give you a very simple example for all of us to understand. Okay. Um, I asked my son actually go and just do a simple mathematics. Okay. So he went to that particular maths textbook. He solved it and came back. Okay. Again, I would ask him, hey, can you solve another problem? Okay. He's going and solving it. Okay. There is a scenario where I would actually put it like, I ask him to, hey man, can you just tell me the number tables? He tells me the number tables like anything. Okay. But when I ask a new number table, which is something different, he is not answering it. Then the question comes to me, what happened to him? He is able to answer all the number tables until 2020 or 20 numbers, but beyond 25, he is not able to do that. So that is where I want you to really make a difference between, okay, by hearting and learning. Okay. So by hearting is a concept where I just muck up everything and I do not implement any kind of a learning about it. Okay. I'll give you another example. Okay. So I actually built a good robot, okay, that has to pick up something from my dining table and just has to serve it to me. Now, when I ask about that particular product, okay, which is something like the robot has to apply some grip. So I told, okay, go and get that apple. Okay, she's able to get that apple. But when I asked her to, the robot to really go and grab that glass of water, then when it is actually picking up that brittle glass, it was breaking. It was actually applying the same kind of a force that it was applying on an apple. But the actual learning here is that, all right, this is a completely different set of material, different set of position or shape. So that learning, is completely different from the learning just go and grab it. You guys have to identify the subtle differences between it. That learning is what we call it as a reinforcement learning aspect of it, which is the outcome of the reinforcement learning. Let us say I'll teach you how to drive a car, and tomorrow I'll give you uh, a truck. You are able to drive it. Okay. So humans also develop this one every day with the continuous interactions with the world. They develop certain kind of learning. So the reinforcement learning is the easiest subject that one can easily absorb because every day we are experiencing it. Okay. So now in all these things, before we actually understand this particular reinforcement learning part of it, understand that intelligence, this definition is not at all very, very well defined. Okay. Suddenly in 2022, 23, you people had started seeing this chat GPT kind of a softwares. Why not they were there earlier? Why now? Okay, is because they have actually built those systems with this framework of reinforcement learning. Okay, now take this example of a robot which is sitting down here. Okay, now the car is coming and it is actually doing that painting there. Now instead of the car, you put a truck. Can this robot does that? No, no. Today's systems are actually developed in a way that it can do only certain aspects of it. I'm writing a code, Python code, that can actually solve only today's thing. But tomorrow, if I want that system to really learn by itself based on the situation, if it is not doing, then it's failing. Correct? So that is something like the most important subtle difference we all have to have before we get into the understanding of this one. Okay. A very simple way that people call it AI, everyone has their own definitions, but how some people had defined is like, there are two dimensions. When I went to LG showroom, TV showroom, I asked that, hey, how much this cost? This would cost 80,000 rupees. How much that cost? He tells like a 2 lakh rupees. Oh my God, it's almost like two times. Why? He tells us, sir, that is AI TV. Now, whenever anyone tells this is AI, this is not AI, as we are all in this particular era, it's always we require a kind of a framework that can actually help us to identify what is AI, what is not AI. Okay. So this is something like I follow. If you people are also comfortable, yes. So now agents that think optimally, okay, agents that think like humans, agents that act like humans, agents that act optimally. These are the four quadrants I actually take. Okay. What is the difference between optimally and human? These are the two different things that we people have to understand. Because whenever we get into this RL part of it, reinforcement learning, RL, I use the word, reinforcement learning part of it, we have to think optimally. First, I'll give you this one. I designed an unmanned car. I asked it, hey, can you take me from here to the airport with low cost? Okay, optimal cost. Then it tells that consider it done, sir. Then it will take me to that optimal cost. It is going. Okay, good job. Now to the same system, I will go and say that, hey, today can you take me to the same airport? Okay. On the way, a heavy rain and some other accident happened on the road. Okay. It could not reach that. It was actually the heavy rain, the water is there, and it was not able to do. But it is always thinking optimally. If it is human, if it is human, what he will do? Oh my God, here it got stuck. There is another road. I will go that route. You understand the difference? I'll give you another example. You entered into the elevator. You wanted to go to the fourth floor. You press the button. It will take you to stop at the fourth floor. Good job. In the same elevator, when I press the same fourth button, okay, my son's hand is outside of that elevator. Okay, but that agent is not worrying about like, hey, someone's hand is outside, some accident can happen. No, it is trying to execute that optimally. It is not thinking like human. You guys are understanding? Okay, so it's not, it's a thinking like human means that decision making is not there. So most of the systems that we are building today are optimal systems. You go to a bank and apply for a loan, education loan, they would look at all these things. Sorry, sir, we can't give you the loan. That is how one system. But if it is an intelligent agent thinking like human, looking at it, wow, I know that he doesn't have any money today, but I can predict that he's able to take a very big position in the top of colleges, Ivy colleges, and the top companies, and his salary will be something like 250K US dollars. I would give him the loan. You understand the difference, guys? So today, bank, you go and apply for the loan that you are getting is a completely defined an agent which is thinking optimally. Or and another one that we want to design that, hey, this particular Kumar is going to have a great job, so give it to him. Such kind of intelligence is what we have to develop in the future systems. Not only there, you have to really implement these systems. You had already seen those systems coming up when you're using all these big language models and you're using other systems also. This was not there. This was not there before before ChatGPT was there. But ChatGPT is the one which is having this reinforcement learning framework, which interacts with the environment and builds that. For example, you and I are building a ChatGPT here, and this is what the complete text about the environment. It actually senses and acts in that environment. It tells that, hey, can you tell me where exactly the Taj Mahal is there? I would like to visit that. And when it was, so you are asking a lot of information. How the people are actually interacting with the agent, that system takes the data and puts into the RL framework. Okay. So now you can actually try with all these different examples. I would put machine learning is like a optimally, thinking optimally, because these are all machine learning algorithms are not intelligent enough like humans. Okay. Machine learning is still like a thinking optimally. Okay. And aeroplane or autopilot is like acting optimally. Okay, it knows that how to land optimally. You want to say something, Kritik? Okay, so if you observe all these movies, okay, I'm taking these examples, okay, there people are actually trying to accomplish this kind of an intelligence in the systems. Are we really going to accomplish it? For all these things, the underlying framework, how it is actually going to come, is what we are going to discuss today. When you look at this AI movie, which is released in 2002, 2003 times, a baby was actually made, a baby robot. This is the baby robot, and trying to give the emotions, because when you are expecting any AI agent to think like human and act like human, okay, then can we really give those emotions? You may have seen the movies. Based on these movies, you may have seen one Indian movie, South Indian movie, which is Robo, by the film star Rajnikant. Okay, you may have seen that movie. There you can actually identify the subtle difference between the intelligence part of it. There the professor wanted to test whether this robot is just following the instructions. Okay, it is just following the instructions. It is not having any emotions. It will ask it to run, 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 run. The robot runs and go and kill your master. It is about to kill the masters, about to kill the masters. Then the professor tells us stop. So, which means that particular robot is just following your instructions, like an elevator, which is taking you to the fourth floor, fifth floor, sixth floor. But if I'm getting a heart attack in that particular elevator while going up, elevator doesn't know whether Madan is getting heart attack or not. Its job is to just go to the fourth floor. Do you call that one as an intelligent? Or do you call something intelligent which stops at the immediate floor and sends the siren to the nearest ambulance and the security? Hey, there is a person who is actually suffering from heart attack in my elevator. You understand the difference, right? So in the same movie also, if you may have observed that Robo movie, you may have observed the robot was not taught the cultural grounding of it, like while trying to protect the people in the fire accident, that robot was carrying a woman who was actually taking bath. Okay, no emotions, no cultural things, with which what happens is that in that movie, if you observe that woman commits suicide by just going opposite to that truck or something, and also in the same movie, he wanted to give that emotion to that robot, that star. Then it starts developing such kind of an affection towards that actress in that movie. Why am I telling all these things here is that the objective that we are having in all these algorithm that we are actually building, right? How we can actually give that intelligence in such a way that can actually think like human and act like human. So people started with this AI. Some of them actually utilized computer science, philosophy, mathematics, cognitive science, linguistics. So many people, when they come to me, hey, Madan, I want to do AI in this one. Which branch should I take? No, for AI, no branch. Any branch is a good branch. Okay, because AI is the easiest topic for all of us because we are experiencing it every day. How I am thinking, can I give the same thinking to my robot? Okay, so I don't want to get into all these details because the time is very much limited here. But I would like to quickly see that when we were actually trying to prove that it is something like an intelligent one, whether it is not intelligent one, people had come up with the different kinds of tests. You people may know this Turing test. Okay, Turing test is the one what they want to say that the most of the intelligent systems that we are building are not intelligent enough. So what they had done, the simple test here is that there is a person inside the room which is locked, and there are two people outside who are writing something in the Chinese and sending through this door. That person is actually responding in Chinese back to that. Okay, then these two people thought, all right, this person knows Chinese because I'm giving questions in Chinese, he is answering in Chinese. They opened the door and they started talking to him in Chinese. But the person tells, I don't know Chinese. So that means he is using some dictionary here, and using that dictionary, he is able to answer it. That means he is not building that intelligence of it, but it just like I gave you the example of my son who is by hearting it. In the same way, he is actually responding to it. So then they decided that any people claim that this system is thinking like a human, they wanted to pass this Turing test. ChatGPT passed this Turing test. Okay. So there are so many debates. I don't want to get into this, but I wanted to give this understanding of like what exactly the intelligence is, like how human perceives. If I go to South India, I can see two languages, two different languages, and I can actually looking at it, I can say that this is different from this, but I don't know which one is what, right? So, which is something like without having that semantic understandings of it, whatever the one that I have is not intelligent enough. Okay, there are so many approaches that you see here. People trying to build different systems. How do I really build intelligence from the natural evolution? Okay, Darwin theory of evolution, which is what the evolutionary algorithms come into the picture. That is my core area where I had done my PhD in evolutionary algorithms, how we can actually give the intelligence. The intelligence that I have today, okay, is actually coming from my mother, father, and my mother's father. Like this is something like so many generations, okay, mutations and crossovers. We are actually into this existence of it. So similarly, based on this particular evolutionary theories, we can actually build this intelligence. Why am I telling this one? Evolutionary algorithms are the best way to build the reinforcement learning framework. The reinforcement learning framework, you always wanted to improvise your knowledge by interacting with the system. The best example is if you have a nephew or niece or your families, any small babies, you observe that when the baby is actually falling, cry, and when they're walking, people clap it, based on that, they actually build that kind of a learning. Oh, if I run like this, then these people are clapping. Okay. So something like that is the framework that actually we see every day. Can we give the same kind of a system to us? Okay. So I'm just quickly going to the actual topic. Okay. First of all, we are calling it as a reinforcement learning. But what is learning, first of all? Okay. A baby who is just born, okay, who started mimicking, okay, by looking at the father, okay, and the father is actually in the tongue outside, okay, the baby is also able to do that. This is unconscious mimicry. So this is a kind of a mimic that is already actually implemented, built in the babies. Now, let us say a mosquito which is actually sitting on your hand and trying to suck the blood, which is also kind of how to suck the blood, is also learning. We call this one is also learning. As I mentioned that a person who knows what it is 29 by 29, okay, and also can work out on the other numbers. All these kinds of learning. Tomorrow, when you go and build any reinforcement learning system, when you join big companies or any other laboratories, you and I need to understand that what is that learning that I'm actually giving to the system and how am I giving. There are two things. What is the learning? Yes, someone raised the hand. Sangeeta, please.
Yeah, sir, just could you elaborate the previous slide? What is 29 by 29, 17 by 20, 17?
Sure, sure. Yeah. So for example, if I give you an instruction like a 13 by 13, okay, you will be able to give the response like a 256, for example. Okay. And if I give you like 18 by 18, what will you do?
Yeah, I'll have to work out the, procedure. I mean, it cannot be just rote learning. Either rote learning or it could be, the procedure, how I arrived at the previous answer, and then I replicate the same thing. And
Correct, exactly. So now what happens here is that if you and I can understand that the logic behind of 29 by 29, that same logic, if I can transfer to the other set of numbers, then I call it as a learning. Okay. For example, when the babies are actually born, okay, they first actually the learning one wise, they don't know who is mother, who is father. They know only one thing. It is proved that this is moving, this is not moving. Okay, this chair is not moving, but someone is moving. So then they actually build that kind of a learning first. Then they will start. Then they'll start applying that logic to all the moving objects going forward. Okay, then they will start applying the logic of how the legs are moving. What I'm trying to bring here is that most of the learning here actually is nothing but how do you really apply the logic that you learn from one place to the other things. That is what even we are doing. For example, hey, I booked my flight ticket, okay, and will that flight land at the right time? What we do here is that, hey, I had seen in my past 10 years, 20 years, this flight delays only by 5%, which that 5%, how I came out with something like a learning which is there in my mind. That people are trying to put it in some mathematical forms and different ways, but that is what I meant by learning. Did I answer your question, please, Sangeeta?
Sir, yes, but I wanted to just go further. Like you have put some the equations also here, interestingly.
Mm-hmm.
So, can you relate these? I mean, with the reinforcement learning?
No, 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 no. I haven't gone to the reinforcement learning yet.
Okay, okay.
Yeah, yeah.
Or
But
transfer learning, or transfer learning.
yeah, transfer learning, just a learning part of it. I'm talking
Okay,
about
okay.
the mind.
But
Okay.
there are these equations of linear
Yeah.
model.
These equations are actually kind of the representation of my logic, how I'm actually storing that information of all my flights that I traveled in the 10 years. Okay.
Hmm.
It's just a representation. See, in machine learning, there are three components. Let me call it learning. Okay. One is representation. Let us say today I represent it as an equation. Tomorrow you can come and say that, why should I take the equation? I can take a graph. I can take anything. That is a representation.
Yeah.
Second is optimization. And whatever that you are actually doing it, that is the means that representation, you actually put that optimization with the data.
Sorry,
Okay.
so can you repeat that? After representation?
After representation, optimization.
Mm-hmm.
Okay. Optimization is the one which actually takes you to whether your logic that you are actually building it is correct or not.
Hmm.
Okay. Now that's the reason what my point earlier I made it here is that people are actually building a machine learning models, but not the reinforcement learning models.
Hmm.
Okay. Machine learning models are always optimal solutions. For example, I want a system to go from here to the airport with an optimal system.
Hmm.
Okay.
Yeah.
But I want a system that actually take me to here to the airport with a reinforcement learning framework, which actually comes up with the different instances of it. Let us say it is raining. A boy suddenly comes onto the road and I slams the brakes. And any other kind of scenarios that I had never considered in my machine learning.
Hmm.
So reinforcement learning is the one which actually brings this component of continual learning.
Hmm.
For example, people were building models to predict whether should I give the loan to this person or not. And they're not giving any feedback to the system as the people are applying for loans. It is a very static machine learning model, just like a rote learning mode. They are not introducing any kind of a feedback to it. So once you start giving the feedback, then you will realize, oh, this is correct. Oh, this is not correct. Oh, I should go like this. Oh, I should go like this. That continual learning was missing in all the machine learning models earlier.
Yeah. So, can I add something here?
Please,
Yeah,
please.
because yesterday, Professor Reddy he was talking about explainable AI. So he gave a similar example, I recall, where in case of a bank loan application, he said explainable AI can provide recourse, that kind of feedback that you are saying, right?
Hmm.
That was one thing I could relate to. In case of babies, my second thing was, in case you explained about babies, how they learn. So I guess reinforcement learning as well as transfer learning both apply, right?
Yeah. Reinforcement learning is a framework. Reinforcement learning is a framework. Okay. Transfer learning is a method.
Okay.
Okay. Okay. What I meant by framework, I want to make this particular sofa to be the sofa which is next to me to be intelligent. Okay. Then it means what? Many people come to meet me and they'll sit down and they will go and sit down and go and everything. If I'm not putting it in the reinforcement learning framework, the same sofa is just people coming and going, people coming and going. Then one day it breaks. Okay. Now, if I actually give the reinforcement learning to the same sofa, whenever any coming and sitting down, hey, I'm sorry, I cannot bear your weight. Hey, I'm sorry, I can actually allow only two people to sit. So that the objective is the sofa doesn't want to break by itself. you know so the brittleness comes here is that where I'm not introducing any reinforcement in a framework, how it has to learn to say that, hey, you are allowed to sit, hey, you are not allowed to sit. Such kind of an intelligence it can actually implement when it is interacting with the many people who are coming and sitting down. If I build that framework, then it would say that, okay, which set of people can sit down so that I should not break. You're getting a very simple toy example I'm trying to put here. Now the
Yes, yes.
same, yeah, something like it. If you look at this one, you actually teach a great deep learning model. It learns all these things, but it is still, for me, both are the same. It is just like so many weight vectors, but there is no actual evolution of intelligence until I put this one into the real system. I take the same deep learning one, let us instead of two, I'll put a human on the road. Now I actually taught it, hey, whenever human is there, slow down or apply the brakes within this distance. That is the neural network I built. I put it into the car, press the button. It started hitting the people. Why? It knows that whatever it is taught in the laboratory, this is the human, and everything, a small baby or a human on the scooter, a human who is actually just going running. These scenarios were not taught to the system. So that what I do is that I will make it more feedback learning based, which by introducing this reinforcement learning, I should be able to bring that intelligence. Did I answer your question, please?
Yes, yes, sir. So
Yeah.
feedback is very important component of reinforcement learning framework.
Correct. But there is one subtle difference. I'll explain it to you here. Okay. Suppose, let us say, feedback is something like I will go and tell my son, Beta, your maths performance is not great. Why don't you focus on trigonometry more? Why don't you practice all these things? This is the feedback one. Second feedback, second feedback. He comes and tells that, Papa, I got these marks in maths. Then I would tell, okay, take these two chocolates. He tells that, Papa, thank you. He goes back. And he comes up again, Papa, I got this one. I tell him that I don't tell him anything. I don't even talk to him. I gave him something like two chocolates. This time, what I do is that I take two chocolates from his pocket. He cries. Okay. Then again, he goes back. He does something. He comes back. Whenever I am taking the chocolates from him, he actually thinks that something I have to improve. What I have to improve? That he finds it out by himself. Not explicitly, I'm telling that you need to do this trigonometry, mathematics, physics, these things. I don't tell him. So, reinforcement learning is the one where you don't explicitly tell that this is what you have to do. There, you just give thumbs up or thumbs down, reward or penalty. And the system itself will actually update by itself to maximize that reward. I hope you guys are getting my point. If I'm giving that to do this trigonometry, do this one, then that is supervised learning. I'm acting like a master, telling that this. I'm not teach. In supervised learning, I'll teach him that what to do. In reinforcement learning, I don't teach him. I'll give him the heads up and heads down. That is the reason reinforcement learning is the best framework for our kids also to perform better, because what I learned 10, 20 years ago, I tried to rub on my son to do the same thing. But he may have another great neural network compared to me, next generation. He may learn the systems much more differently than me. And hence, if I do the reinforcement, he learns much better given the situations and scenarios than I'm telling him that beta AC drive karo. When he's driving, AC karo, AC karo, AC karo. No, that is not going. When he's driving, I'll tell that good job. When he's not driving, well, bad job. Then he himself finds it out. That is what the actual reinforcement learning component I would like to talk here. So when we get into this one, supervised learning, yeah, yes, madam, please.
Yeah, just to take this example, sir, I'm sorry I'm taking a little time, but
No
just,
problem.
yeah.
Yeah.
So, does it not presuppose that the agent to whom we are giving this feedback, they are very mindful and thoughtful, and they are able to infer, in what cases they are getting that so-called reward, and in what cases they are getting the so-called penalty, and then they infer from it, and then they modify their behavior. So all that supposes a lot of intelligence and mindfulness, and even in humans.
That is so obvious with humans, what you're telling,
Yeah,
because that is called meta learning.
yeah.
I always I predict whether my papa tells upside or downside, right? Which is something like learning to learn. But that is so obvious in humans. But if I actually build a credit card loan system that I actually implement it based on the data that I got, I just built the system. Some bank manager told me, hey, our bank gives this. He's introducing first a supervised learning approach. Then I build a model. I'll put it into the Citibank or State Bank of India. Until ChatGPT made this big kind of a leap in terms of intelligence, everyone was just taking that model and just thinking that hamara kaam ho gaya, just I'll keep it here and it will do everything. No one was actually building that framework of I am rejecting a air 14th rank person's bank loan. That system doesn't know. So my point is that systems are actually built like that. Now once you build the system, like with the supervisor, that's fine, you put into the system. Now you have to introduce this reinforcement learning framework, but I'm going to discuss about what are the scenarios that we should consider to really do that. Okay, just sorry for it. Yeah. So now when it comes to the reinforcement learning, okay, I'm sorry, this is something like just a minute. When it comes to the reinforcement learning, okay, this is the environment. Okay, this is the environment. I have put it like a robot here. Tomorrow it could be your own Python program. It could be an elevator. It could be a car. It could be a baby. It could be anything that you want to build the system. Okay, which I call it is an environment. Okay. Now what happens here is that this is the place I want to have an agent. Earlier, human was there. Human knows how to take decisions. Now, in his place, I want to put this agent. Now, what this agent has to do, this agent has to understand the environment. For example, how I can actually perceive this environment. One way, computer vision, I'll put two cameras to the agent so that it can see what is happening. I can actually put some sensors, other sensors like touch sensors, whatever you wanted to grab the data from this environment that you can put it. The best example you can take unmanned car. An unmanned car is having near about like a 26 cameras, 360 degree. It can see right side, left side, who is there, what, and everything. All the sensors data is the data that it is actually taking. Now, I'm taking this example of unmanned car because we are all aware of it. Okay. Now, what happens is that I actually want to teach this agent to learn how to drive in urban environments. Let us, I'll take Bangalore or Jabalpur, Delhi. Now, in order to teach this robot, what I do here is that, hey, you identify this person, just like I told my son, right? He came with the maths and I say thumbs up, thumbs down. I put this car here. It starts killing the people. Then I'm doing the thumbs up down. And it is not killing the people on the road. Then I'm doing the thumbs up, which is costly for me because I'm killing the real world people. So why can't I just create a kind of a simulation environment? That is where people go to simulation environment, give the same kind of scenarios of the roads and frictions and everything to the road and mud and water, potholes and everything. They will try to tell that, okay, you do it and apply the action. I will give you the thumbs up. So this is a kind of a loop that goes where every time it does a good one, I'll give you reward. I don't tell that go left, go right. If I'm doing that one, that is the previous one, rule-based one. If the system actually develops that kind of an intelligence by itself, for that, I can only do that thumbs up, thumbs down. Okay, let us see an example here. Okay, this is something like one robot. Okay, and just to see that how this reinforcement learning will be given here. You people can hear the sound, right? I have to share the sound or share the sound I have to do here. Um, share the sound. How do I do the share the sound? You people can hear the sound, please.
This is Mr. Babin.
Can you hear the sound,
Yes,
please?
sir, we can hear the sound.
You can hear the sound. Thank you so much. Yeah.
He owns a bar. In earlier times, he enjoyed tending the bar himself. Last Christmas, his mum bought him a Wii. Since he enjoys playing Wii more than working, he isn't spending much time at the bar anymore. This is why his mum bought him a service robot for Christmas. His name is Shaker. He's an all-round service robot with some amazing functionality. Some of the things he can do include recognizing faces, recognizing places, picking up bottles, and transferring virtual money to his owner's account. The problem is that Shaker does not know when to use which skill. Mr. Babbage could hire a bartending expert to program Shaker, but that would cost more than he can afford. So, instead, he decided to buy Shaker an inexpensive, ready-to-use reinforcement learning module. As in all reinforcement learning scenarios, the task is specified implicitly through the means of a numerical reward signal. Shaker receives rewards or punishments based on the actions he takes, and his goal is to wisely choose his actions so that he maximizes the overall sum of rewards. Defining the rewards for the bartending task is easy. Every time a customer pays, Shaker receives a reward equal to the amount of money paid minus the amount the bar had to pay for that drink. Since Shaker is a general-purpose robot, he knows nothing about the specific task of bartending initially, so he starts off by randomly selecting among his limited set of actions. For Shaker, this means a lot of punishment, a lot of pain. However, all this pain is not in vain. It provides Shaker with useful experience which he is constantly learning from. Shaker uses a well-known reinforcement learning algorithm called Q-learning. Q-learning will enable Shaker to decide what action to select in each situation. In reinforcement learning, we have the notion of states, which basically correspond to situations.
Q-learning also uses the concept of a value function. The optimal value function tells Shaker for each state S and action A how much total future reward he should expect by executing action A in state S, assuming he behaves perfectly from that point onward.
For example, the optimal value function for the state, in front of customer, bottle in hand, and the action, deliver drink, is high. After delivering the drink, Shaker only has to collect the payment in order to get a nice positive reward. Once the optimal value function is known, action selection becomes easy. Shaker simply has to select the action with the highest value. Let's see how Shaker will learn the optimal value function. Assume that the value function is initially set to 0 for all states and actions. This means that Shaker randomly selects among his actions because the value of all actions is 0. But imagine that, after a lot of random walking around, Shaker ends up in the state, in front of customer, debit card on table, and chooses the action, accept payment. Upon taking this action, he receives a positive reward. As a consequence, Q learning will increase the value of action accept payment, and Shaker will be more likely to select this action in the future. Using Q learning, Shaker learns about more than just immediate rewards. For instance, when taking action, deliver drink, in state, in front of customer, drink in hand, Shaker receives no immediate reward. However, after taking that action, he ends up in the state, in front of customer, debit card on table. He already knows that this is a good state because the value of action, accept payment, is high in this state. So he learns that the value of action, deliver drink, should be increased. In this film, we left out many technical details about Q learning, as it assumes that Shaker.
So I'll stop here. The reason why I'm giving this practical example here is that you may have observed one important thing here. Okay, whenever someone approaches you and tells you that asking you that, hey, can you just build a reinforcement learning framework? Okay, first thing that we have to do here is that define the scope. Okay, define the scope. That is what I'm going to give the examples in the subsequent slides. But with respect to this one, I want you people to just understand how it is actually. Okay, the scope here is that only the bartender here, he has to serve the customers. That's it. If you define another scope, like you go to a restaurant and not only taking the order, you also ask him that, hey, my baby is crying, can you just entertain him? That is out of scope. Okay, so anytime that you're actually building an agent in unmanned car, that algorithm has to be defined with the scope. This is what it has to be done. Otherwise, the problem space is so big and you will never solve that problem, number one. In this particular one, the scope it is clearly defined is that it is a bartender where he has to recognize the faces, serve the drinks, take the payments. Okay, it's very clear. And many times people expect some new kind of thing happens, then you have to define your problem space. We'll go into the details, number one. Number two, there is one interesting thing she mentioned. One is that what is the action that is done by this agent? Okay, he's the robot agent. Okay, Shaker is the robot agent. What is the action? When he's doing that particular action, what is the state he's in? So this is what reinforcement learning always plays with. What is the state you are in? What is the action you are in? Let us deep dive into a few examples so that we can understand here. Okay, I'll take a completely different example. Now, a bank approached us, okay, 80 years ago, asked us and telling that, hey, 2008 recession? He said, yes, we know. A lot of people could not pay their EMIs, okay, their mortgages. Yeah, government actually put a rule for all the banks to ensure that how many people are actually going to pay, how many people are not going to pay the loan. That we need to submit the report by March 31st. This is the problem statement a big bank approached us. So that time, what we had defined here is that, oh, they gave us the data of last 10, 20 years data, okay, how it happened and everything. When I go and just build a simple machine learning model, then it will tell that whether he pays it or whether he doesn't pay, whether he pays it or he doesn't pay. My problem is solved for that year. Next year, new people come, and again I have to go and get the new model I have to build. Again, in new scenarios, because banks changes their policies and everything. Then how many models I build? If that is the case, all my life I build the models. Then what we thought is that why can't we just build this reinforcement learning framework? So I just wanted to throw that how we are actually approaching the problem here. If it is something like a model that I build it to know whether this particular product is a good product or not good product, that product may stay for 10 years or 8 years, 5 years. I don't have to update my model. But if it is actually varying, new products are coming to the market, every time I have to build the model, right? This is the best case. If you just imagine that Amazon, you are there in Amazon, the machine learning scientists sitting down there, their job earlier, they used to every day update the recommendation algorithms because the catalog is getting updated and everything. So just try to understand the problems where it is. Now, for that bank, what we had actually defined here is that we actually defined Madan is a person who is paying his EMI so well. All the 9 months he paid, last 3 months he did not pay. Now tell me, what is the probability that he's going to pay or not? Okay, you would put some kind of a probability, some 75% or like that, he pays it. But after 3 months, again, he paid all the 3 months and the fourth month. Okay. Like Madan, there are some 10,000 people who are paying sometimes, who are not paying, they're paying 2 months and then not paying, again paying, and like that. There are so many scenarios are actually coming into the picture. There, I am in the state where I paid from the last 9 months, but did not pay 3 months, is my state. Okay, is my state. Now, next month, whether he pays it or not, that action. Okay, so point here is that what I'm trying to make here is that in this particular shaker bartender case, the state here is that he's putting that bottle there and taking that one. Okay, the state where he's actually receiving that particular payment card, the bottle, and the action that he has to deliver that right Coke or what it may be. How do we ensure that the system is always taking the right action at the right state is what this framework is trying to solve. Similarly, an unmanned car is going on the road. It is in the state that observed a human standing on the road. The action here is that should I move forward or stop here or go slow or estimate the speed at which he is coming? Should I really slow down? The action here is that where I have to slow down or should I move? The state in which I'm here, there is a person standing. A baby came onto the road suddenly. The action I take is slamming the brakes. How exactly this intelligence can be given to an unmanned car? Which is something like we have to come on, we know that there is a reinforcement-led framework. In that framework, we always try to maximize the actions, those are all leading towards reward. We minimize the actions, those are leading to penalty. Okay, so in this case also, how do we ensure that whenever he's asking, delivering the right one, that score is getting maximized, reward score is getting maximized, then he's happy. Otherwise, he's sad, Now, with this example, this is what we need to really identify. The objective should be clear in the reinforcement learning problem. The objective should be clear. The scope should be clear. Do not define the scope is something like completely open, with which what happens here is that you will never solve the problem. For example, I designed this unmanned car only for my Bangalore, for my sector 24. Okay, I know that complete space and I can teach it. If I go and put it somewhere in Chandigarh, it may fail. But there again, I have to do some trial and learns and that feedback and everything that has to go. Okay. But everywhere, the way we want to define the scope, the objective, reward is positive or negative. You can define this reward positive, like let's say 3 chocolates, 5 chocolates, 50 chocolates, or 2 chocolates when you're taking the penalty. This is a very interesting thing that I wanted to emphasize. Remember this one, very, very important. You are just giving a scalar signal, but not a decision factor. As I told you, I don't tell my son that go and focus on algebra, go and focus on trigonometry. I don't tell him that. I just give him the signal that, hey, can you really just improve positive or negative? So that my son actually builds that, what should I do so that I can maximize my reward? He himself takes the decision whether should focus on trigonometry or algebra. No external person has to do that. So in reinforcement learning, you will never tell them that the decision factor decides what action to take. And ultimately, the agent here maximizes that cumulative reward. That is how the reinforcement learning happens. Okay. I'm sure you people got very fair understanding of this one. Any questions, any discussions, please, before I go to the next. Anyone? Right. Yeah, I think good.
Okay, sir. Yeah.
Yeah, we can move, right? Yeah. Thank you. Thank you, madam. Now, you know that, okay, these are all the observations. And I'm trying to building an agent. As I mentioned, please do not think agent means only for the robot. Think a bank application. Think your own regular assignment that you are doing. Okay, you want an agent that has to complete your assignment, or you want an agent that has to maximize your availability for your students or for your family or for your friends. Build an agent that has to really help you to schedule your day. Okay, build an agent that can actually take care of all the financial markets ups and downs or whatever it may be. Build an agent which can actually maximize your investment returns. You take up whatever it is. Okay, agent can be applied any of these scenarios. Physical one is robots, yeah, that you can think. But the framework that you're actually going to design in financial world, in banking world, loan application is one scenario I gave. In physical scenario, I gave you the robot. In your own scenario, you can do. But all these things you need to depend. But ultimately, if at all you wanted to do this one, okay, as I mentioned, it has to know two things: state and action pair. Which state am I in? What is the action I have to take? Which state, which action? Which state, which action? I started, the unmanned car started at my house. Which state? At the origin. Action, move forward. Okay. Another state, a person on the road. Action, stop. Again, no person on the road. State, no person on the road. Action, move forward. Like that, state action, state action, state action, state action, state action. Like that, you will get a very big set of state action pairs for you to accomplish that. It will become kind of a graph in front of you. Just imagine a set of state action pairs in front of you based on the scenarios where to go and everything is defined. Now, the question here is that what is the best state action pairs I should take so that I can maximize my reward? Right? That is what we have to define. I am at a state 1, my house. I am at a state 2. What should I do? Now here, I'm getting into one more level down. I am going for a war against a country. There, I don't know the situation there, the complete environment I don't know. In Bangalore, I know in my sector, I know where exactly this turn comes, where exactly the tree is, where exactly the road. I know all these things. But when I'm going for a war against another place, or I go to another country, then I don't know that. So when I don't know the complete entire states of all the environments, then it's very difficult for me to really understand because I don't know. If you know, let us say, okay, if you know the complete states of that one, for example, for the bank example, we know all the states. whether he pays it or not, whether January, February, March he paid, and April he did not pay, and again in May month he paid both April and May. We know all these things because the complete full system of the environment I know. And in the cases of some examples where I'm going to an exam, okay, and I don't know what are the questions those are actually going to come, okay. And at least if I know the state of the environment, let us say only physics questions, then I know, okay, from physics, this chapter, it will come. But if I don't know the complete set of things, then it is a kind of an unknown information. So there are two things here. Agents would have the complete understanding of the system. Agents who doesn't have complete understanding of the systems. Okay, that is called fully observable environments and partially observable environments. Okay. Now, what is policy here? Now I'm getting into a little bit technical things because this reinforcement learning is a big course which requires like 6 months of course. So we cannot cover everything in detail. So that my objective here is that I just wanted to give a fair understanding about of this reinforcement learning, where it can be applied, what it is. That's my objective without getting into the details so that you can practice it by yourself. Now let us say policy means the best policy. Okay, policy means immediately for all of us gets the trigger in that insurance policy, okay, or travel policy or some government policies. Yes, those are all the right words. Okay, policy is nothing but, suppose an insurance agent comes to my house and tells me that, hey, if you pay this one, by the time your son graduates, we'll give you this much amount. Okay, so he defines a kind of a policy. He puts a policy for in front of me. Okay, when your son goes to this state to this thing, we will give this much amount. When he graduates, this much amount and this much amount. Like that, he is actually defining a policy for me. Now, I'm talking about the same policy for unmanned vehicle robot. The robot is actually there in my sector, and where it has to go from one place to the other place. I would actually wanted a policy that it has to go to the end of the street, uh, throw all my dust over there and come back home. Okay, it is fully observable environment because it knows that the complete our sector, it knows which gully, which one, everything it knows, so it can do that. But what is the policy that I want to do? So I started using it, and hey, don't harm anyone, my objective. Hey, do not, I'm not trying to teach that. Okay, these are my objective functions. Okay, then I actually started telling that it's better if it actually reduces my battery. Okay, the consumption. So I define some objectives. When I define the objectives, okay, at the end of the day, the agent will come up with a kind of a behavior which tells that this is how I would go to that particular end of the street and throw it out and come back. That automatically it identifies it. So now, in order to do this one, what I do here is that I would actually define a function. Okay. The function here is that I would tell that agent in this particular state, hey, Madan, I am at this particular junction. Okay. I think that junction is so complicated. That value function tells that if you are at the junction, it takes more time for you to go to that your goal. So value function always evaluates the state where you are in. Okay. Now, suppose if I tell them, hey, you are at the right state, then it will tell us that, okay, now it is the right state. Should I go left? Should I go right? Should I go forward? That is the set of actions. Okay. So the value function tells that whether that particular state is right or not. Now, in order to get the good optimal policy from the agent to execute it, okay, like the same shaker example, if you take the optimal policy, what is the policy they're expecting? Recognize the face, pick up the bottle, serve it, take the payment. Okay. In order to do this one, they have defined multiple states. Now, the state at which you are there, okay, holding that particular payment one, that means the next action is that swipe the card or take the money. If you are doing that particular action, that means I'm actually getting more money. My reward is I'm giving you more reward, so that you are actually taking that action and more and more. Are you guys getting me? So that value function actually tells that this state is correct or not. For example, I will tell you another state where the customer is sitting down, the robot is looking at the upside something. I would tell that that state is not a good state for us. Then whatever the action that you take is not helpful for me. The customer is sitting down there. The best action that you can take here is that talk to the customer and take it. You're guys getting me here? So now what we wanted to do here is that we wanted to maximize this value function so that it will go to the right state. Okay. And where exactly I should go corresponding to that reward is what we want to do. For this is very, very interesting thing. Okay. I want to talk about this concept. It's a very, very important concept in the reinforcement learning. Exploration and exploitation. Okay. Exploration and exploitation. This is I will try to give a very a simple example so that you can actually store it in your mind easily. Sometimes my father comes to me and tells me that, hey Madan, uh, you want to take the money from me now itself to buy your car, okay, or you want to wait for 10 more years or 5 more years to buy something like private jet. Okay, I'm not rich, I'm just taking this simple example. Okay, then I would actually think, okay, should I take this car now or should I wait after 10 years so that I will get that jet? This is what even in insurance policy also people tell. सर अगर आप पैसा अभी ले लेंगे या 4 साल के बाद ले लेंगे, 4 साल के बाद ले लेंगे तो इतना पैसा आएगा. So they actually try to give kind of a scenarios for you. One is now or later. Okay. So what happens is that if it is now I'm taking, okay, now I'm taking, that means I'm not exploring further. It is something like you go whenever you go for trekking or any kind of new places, people say, tell that, sir, you want to go there or shall we go back? Which is something like there is something you can see. Okay. Yes, I want to explore further so that I will get the more information and I will explore more information so that I can maximize my reward and so that I can actually have a better policy for me. Okay. So whether you wanted to really take that information, okay, exploration, and by like exploration, you wanted to really take the decision now or later is what this exploration exploitation. When we are designing the agents, we actually really see that can you explore more? Can you explore more? Even after the more and more explorations, sometimes reward doesn't go up. Then what we do is that, okay, I think this is the max we got it. Let us actually use this one. And whatever the reward we got it, let's go back home. So that is how actually that is one more interesting framework that exploration is coming. Exploration and exploitation. Just keep it in your thing. Most of the research papers, when you read, people mention this exploration and exploitation is the framework we are using. That would help you. Okay. Now, quickly getting on to the RL and planning. Many times people actually get confused with these two words. Okay. People tell here is that I have a great plan. Okay. To go from here to somewhere to have nice family dinner. Okay. I have a plan. I'll go morning with my kids and I do this, do this. This is a plan. Okay. I know the complete things. Whereas in the planning environment, okay, you wanted to really do any kind of reinforcement learning there, I think it doesn't make sense because it is completely known to us. You know that what to do, which is something like you have a policy already in your mind, okay, and there is nothing that you can actually apply. Okay, I'm not saying that nothing you can apply. This is something like my understanding can be applied. That is another debate. I don't want to get into that now. Okay, so try to understand one thing. In this particular RL, the environment is initially unknown to you. Okay, First, I'm building the agent. I have to teach that more one. This is our society, and this is our sector, and this is this. I have to tell that, and I will have to really, my agent has to interact with the world. Okay, then it improves its policy. That is reinforcement learning. That is the learning part of it. Now, planning here is that the model of the environment is known. You know where to do, what to do. And from this place to this place, you have to go. This place, this you have to go. It's a plan, which is a series of steps that you know. Okay. And there is no interaction in this one. So many times, robot motion planning, robot path planning, when you are actually telling that, that you don't have to do anything. It has to pick up this particular one and keep it one. I'm actually designing a path plan for this robot. I'm designing a path plan for this one to go from point A to point B. It's a clear planning. But if you want to really bring the environment, in that environment, you want to bring some kind of a new way of executing a new plan, yes, then you have to introduce the reinforcement learning framework. Okay. Now, as I mentioned here, there are two things. One is that I know about my society, which is something like I know about the model of the environment. I'll quickly jump onto another example so that you will understand. A chess game, which is having 8 by 8 grid, okay, which is completely known to you. Completely known to you. The game that you're actually playing, the number of moves and everything are completely known to you. Okay. Whereas model free method, where you do not, I would put it like this, you do not have the complete game. You don't know the complete model of the game, but you would explore. The best example is trekking. Trekking is the one where you explore and you learn. Okay, there you don't know the complete model of वो कैसे दिखेगा क्या है and everything. So again, bank example I gave you earlier. I'm giving the bank example. I know the number of states. I know the number of actions. I know that one, which is a kind of very clear, so that I can model that environment, and hence I can actually do this reward and everything, reward or exploration, everything. Model free environments are like, hey, is this the first time that you are coming? Yeah, I'm first time. That means you don't have any model about that one. You are going to explore that. Okay, so these are the two different things. Now, just understand here, model free, what you do always the trial and error. Okay, model based, you first know that complete model of the environment, you know the complete society, you know the complete chess game, you know the complete one, then you actually plan it. Okay, and you need a kind of an environment of the model. Yes, it learns. Okay, or some dynamics that is called probability transfer matrix and everything. Okay, there is no knowledge of that. Okay, see, this is what I told you. You're riding a bike by practice or learning a cycle. Okay, which is something like there is no model of what you are actually doing. Okay, and like watching a tutorial and simulation, and these are all some examples I have given here. Okay, so first here in the model based, what it is that first you understand how the environment works, how the model is that, then you drive the policy. Here you actually learn while doing this trial and error in the real time, the model free ones. Okay, now can someone tell me that whether this is like some use cases I have given here? Okay, is it model based or model free ones? Anyone? Even if you can't answer, just watch it and read it. Just tell me that whether it is model free or model based.
The self-driving car is definitely model free.
Mm-hmm. Correct. Yeah, here it is.
Second one is model based.
Which one? Which one is model based?
Second one.
Second one, playing a doom. Yeah, actually, do not try to define like a very strict line. Okay. Both of them are like you can actually combine it also. That methods are also existing, but the reason I'm giving here is that try to get that intuition about what is model based and model free. Okay, that's my point here. Okay, model free. This one, bipedal robot walking.
Model free.
Model free. Okay. This one, stock trading bot. Without modeling the market behavior. That is also model free. The whole slide is model free only. Okay. So wherever you are not modeling that marketing behavior, you are not modeling that balancing of that, you are not modeling the complete pixels, what it may be. Okay, road dynamics, then these are all the model free ones. Okay, the advantage of model free here is that advantages and disadvantages are there. If it is model based, so you know the system by yourself. Like I know my room. Okay. Okay, one example I'll give you. How many of you had experienced this vacuum robots? You may have seen in your friend's house or in your own house. Okay. When I buy that particular robot and brings to my house and keep it, okay, first thing what it does here is that it will build the model of my house by exploration. If you people wanted to just experience it, just go to your friend's house or anything, just to take that vacuum cleaner one. What they do is that the moment you buy that, you keep it in your house, it will go and start hitting the walls and everywhere. And wherever it is free space, it will go. It is just, okay, this is called SLAM. We call it in robotics, okay? Simultaneous localization and mapping. So where it actually tries to build the complete environment. It is just like, when I take my son when he was ninth standard, he goes to his nani's house. He started going to all the rooms. Okay, where is this room? Where is that room? Like that. He goes to all the rooms and everything. He is like exploration and trying to build the model. And later when you ask him, where is your mama? Oh, mama is in kitchen. He shows the direction. Okay, which is something like the same way the robot which we actually bring, it tries to build that environment by itself. And then later you actually apply the policy. For example, hey, go to kitchen and get me the water. And then it should know that, okay, I am currently in the master bedroom. If I want to go to that kitchen, then it uses that model of my house and it designs that map and goes and gets it. In the meantime, someone actually just comes in between, then it has to take the decision how to really do. That kind of learning is actually it is required. So point here is that it is easy for me to construct that model of my house. But let us say with the same robot, I go to IPL match and try to construct it to know that where this particular screens and everything. I know, of course, it is possible. I'm not saying it's not possible, but there it's better for me to explore that world and learn by myself instead of building the complete one. Because why it happens is that from Ahmedabad to Bangalore Chinnaswamy Stadium, when I go, maybe the environment is same, but slightly somehow different. It may work, it may not work. In that case, I better model the cricket ground and go ahead. For example, I want to use the same robot in the cricket ground sometime. I want to go to some soccer ground. Then I better go for the model free. So please try to think that whether you want to build a model or not. Now I know that this particular robot has to clean this car when it is coming. Okay. Then I model that car because this car is of all the shapes. Those are coming to my assembly line. All are Maruti, Suzuki models. So I know. But suddenly, if I take it to Honda, then it cannot work. Then again, I have to model my thing. If I'm the person building a company which I wanted to really do it, then I will go for model free method. So it all depends upon the use case. That's why I'm not trying to tell you here is that this should be only model free. They should not be. It is something like how you actually define that. Now this one is okay. This one is AlphaGo robotics arm control. Okay. It's better to learn that so that I can better plan it because my arm robot is sitting down on the same thing. My environment is known. I'm not moving anywhere. So the warehouse is known to me. The cricket ground is known to me. And only when I move from here to there, then it would change, you know. So like that, you actually define it how you wanted to design your system. It actually helps you to take whether it's model based or model free. Okay. Now these are all fine, but I'm slightly getting into the mathematics of it. Okay. All right, these are all great. Can we mathematically formalize this problem? But before getting into it, I want to add my experience here. Yes, you can do it, but understand one thing. If I actually define the mathematical part of it, then definitely I will be able to get a solution of it. That means there is a solution exists, mathematically proven one. But some scenarios where these mathematical systems, even though they give the solutions, guaranteed solutions, but not scalable. Not scalable. You may have to play the game. For example, for a bank loan system, the number of state and action pairs we have taken that time was only 52. 52 state action pairs. Now just imagine 52 state action pairs. Imagine in front of you like 52 state action pairs are there. Now you wanted to design a policy, you actually do the computation on these 52 only. Take another scenario where that's the reason in the beginning I mentioned this very important point. Define the scope. If your scope is like not 52, it is 5,200 states and action pairs, that is what people think that, Madan, this robot, it is working so well. Can we really put it in the war and win it? No, no, it doesn't work. It doesn't work. I mean, it doesn't work with the RL framework. What I meant by it doesn't work means not something it cannot fly or anything. With RL framework, you can't really do that. Even now, people are actually what they're doing here is that they're manually operating it. But when we launched the unmanned vehicles in Afghanistan in 2012, 2013 times, these unmanned vehicles are actually going to Afghanistan and landing there. Okay, and the people are actually doing with from here, go here, and it was going, but it was getting stuck there. It was unable to come out. There we need RL algorithm. Why we applied RL algorithm here is that we know the plan. The moment the chopper comes and puts those things here, I'll show those examples we have done. That comes down here, and from that particular place, as it is actually going to different things, just like a kid is sitting down, those people are actually doing the teleoperation going there. The plan is there, go from here to there. It's a plan, no reinforcement learning required. No reinforcement learning required. Even the robots that you had seen in the IPL, those are walking and everything. Someone is controlling at the back. Those are not actually having the intelligence of, okay, if Kohli comes this way, and if this guy comes this way, I have to go this way. That is not learned. Someone is operating them somewhere. Now the same one got stuck there in that environment that it got stuck there. We need kind of a human way of actions. How? The moment I get stuck when I'm the driver, I look at back and just I take all these decisions and come out of it. That intelligence we can give it at RL. But now the question, going back to the actual question. In bank, you said more than 52 states that you have taken. It is so good, very well, nice. But in the kind of battle environment, do you really build the model there? No, I don't want to, because I don't know that one. I don't want. Then what do? I actually build the exploration exploitation framework of the RL, so that I will actually see that the optimal policies that I can actually design it in the real time, just like how I'm actually learning the bike, I mean to say cycling, and how I fall and everything using the reward functions and the way that build the policy to learn that one. Similarly, I learn this particular one also to come out. You're getting me? So now, in that scenario, you come and say that, Madan, mathematically it is guaranteed one. Can we build a mathematical solution and do it? I say, dude, I think it's not scalable. It's not scalable. It's not scalable. Why? Because there are so many states that you define, not 52, 5,000 states. When 5,000 states, when you're actually trying to go in the exploration mode to design those value functions, the system, computational system do so many permutation combinations, and you may not get convergence in that. And hence people had this until now I talked about the layer. Now we are actually going into the different layers of it, like scalability aspect of it. When I want to build a robot, it has to do some kind of actions in my laboratory, in my one, we have to handle it different. When it is unmanned car, the RL frame is different. Chat GPT, they also use that RL one. They have your RLHF, reinforcement learning human feedback systems. I'm sure you people are aware of it. They hired in Delhi or China, they hired something like 500,000 people, and they were actually giving the feedback to the questions and answers that ChatGPT was doing. They built a big RL framework. Now today, what ChatGPT is doing, is learning by itself. Whatever the questions and everything that you are giving, the feedback learning system that behind the scenes, that reward and penalty thing is running, and the answers that you are getting here in front of you are actually the outputs of that RL framework, because they introduced that one. You go to the same Google search, you search for that, you are getting, even Google search. Yesterday I was actually searching for GPUs for machine learning in Bangalore. It is giving me the results, which is something like some machines or something. It is still not having that context of it. If I give the feedback to the Google telling that, hey, this is not what I wanted this one, so that like me, another person comes, it should be able to give that. That RL framework is not there yet, at least what I found. I'm not trying to make my comment on that, but this is my observation. Whereas ChatGPT, that you can see that kind of improvement here, okay, how it is actually giving the one by one, it is going to the one state to the other state, one state to the other state, and it is actually accumulating the complete one and giving it as a feedback to the system. Now people are actually trying to define this one, okay, in the mathematical way as a MDP problem, where it captures all the SDPs and which state to go. This is something like you identify this transition probabilities matrix. You just do a simple math, simple exercise at home. You take only 4 grids, okay, 4 grids, and you just construct this transition probability. And you ask which action to take and what action to take. A simple problem on the white paper. You do it. That's it. That is what reinforcement learning. That's it. I'm going to show you one example here. Okay, these are all something like going to the another state and everything. This is the one. Let us say I have taken all the states. States means not the states of like Andhra, Telangana, not like that. Okay, different states of states and actions. Okay, of Delhi from the past 26 days. I have taken only 2 variables. Okay, and this is the transition probability. This is a simple state action pair that you are having. Now you are trying to building an agent. You ask that agent, hey, tell me, in the last 4 days, it was pretty. What are the chances that it is going to rain tomorrow? Okay, then it will actually tell you that pretty and rain 0.05. So this is one of the transition probability. It is actually going to construct on 2 states I'm talking about. If you take a chess, the number of states would increase accordingly. If you take another game, it would change accordingly. One point we all have to remember here, as you increase the number of states and everything for your problem, whatever you are actually doing imagine that you are introducing the complexity into the system. When you're introducing the complexity in the system means it has to explore all the possible states and everything. Now, this is one simple example. Okay. Now, students in a class who are actually attending a class and doing some Facebook, and some people are sleeping, and there some of them are going to the pub, and what is that they are going to pass? Okay. So now you wanted an agent, okay, that wants to replace a dormitory parent, okay, with an agent. That agent should be able to tell whether my son is going to pass or not. Is actually that agent is actually going to predict or going to actually tell me that whether the situation of whether what is that probability is going to be there. So here the episodes are something like the episode is something like it is starting and ending it. Now, this is something like one episode, okay? Going to the class, Facebook, spending in again Facebook, and going to the class and class two, and again sleeping. And this is a very big, long episode. These are all different episodes that you're going to collect, okay, for each student. So, for example, I'll map it to the bank example. If one episode here is that I'm paying, not paying, not paying, again paying and not whatever that I did not pay, that one paying, or only pay that one. So like that, you will get all the scenarios. All the scenarios I would call it as an episode. But here is the point of why I'm talking about episode. Every episode here has a termination, not like infinite one. If it is infinite one, just imagine that you have to introduce into the complexity of your computation one will go up. Okay. So now this is a kind of Markov reward process. Okay. In this one, you will have a state, transition probability, reward, and a discount factor. Discount factor is the one that I mentioned, right? In the exploration exploitation comes. Okay. Let us not get into that. Okay. These are all some definitions. I'll quickly move. Also look at the time. Okay. These are all the different episodes we actually discussed, right? You actually identify what is the cumulative reward for him. Okay. These are all different scenarios and everything. I don't want to get into that. Okay. At this point, quickly, I'll just move. Okay. These are all the optimal state value functions for the same thing. Okay. Yeah. Discount factor, I already told you, discounted rewards. It is also similarly like assistant professor to associate professor, tenure professor, and you take all the transition probabilities. Given that you are the assistant professor for this much duration, what is the probability that you are going to be tenured per person? You build an agent, that agent is actually going to do. Okay. I want to quickly go to the another topic. That's fine. Okay. Yeah, this is what I meant by, okay. If you have 100,000 states, you are solving in 100,000 of this one. It's definitely very, very complex. Okay. Yeah, this is something like a real world example that we have actually implemented. Okay. In this case, what exactly it is that it has to go from one place to the other place. I can't show the real videos. That's why I'm showing these videos here. Okay. Now here, how do I really define this complete system which has to learn unmanned way? Okay, unmanned vehicles should build the reinforcement learning one. If it has to go to the different things, how actually I do the simulations so that I can actually capture different behaviors. Okay, let us say a behavior that is actually climbing up the rock, a behavior crossing through the mud, a behavior got stuck in the sand. If you want to generate these level of behaviors in that reinforcement learning framework, how many policies that I need to generate? The policies, which is something like how to act in a different state and action, is what the complete problem statement here. Okay, we have done all these different environments and building some kind of policies and algorithms to identify the optimal things, optimal turns and everything. Okay, just this is an unmanned example. Okay, MDPs, this is right. Episodic, I mentioned, value functions. These are two. Yeah, dynamic programming. I'm sure this topic is very well known to many of you. So in dynamic programming, as I mentioned here, whenever you are actually getting any task that you are getting, okay, let me take an example here. Now you know that your agent in that war environment is actually doing so well, okay, which is actually there and it is doing so well. So Now you take that particular policy, whatever it is there, and you actually evaluate that particular one, how it is actually performing. Okay, which is something like we have discussed about whether it is raining in Delhi or not. These are all some kind of a policy that is there. You identify that whether this particular person is the right place or not. That is what value function. Okay, and you will be able to see that whether this policy is right or not. Now the same policy, can I really execute it, or should I really improve that policy? Which generally comes to a question that in the bank environment, whether I have to really improve my policy because there's so many different customers are coming to the picture, or in e-commerce, so many people are actually coming and giving their feedback to my services and everything. As the scenarios are changing, the same policy that you have designed by learning all these reinforcement learning one, you may have to improve it. Okay, improve it. So that is something like we call it as a control one. So as I mentioned, there are two tasks, right? That is the episodic task. That's what this one, which has to have a kind of an end to it. Okay, that is why it is an episodic one. And in another cases, there just let me move this one above. In another cases, it is a continuous task. Okay, where it is continuously working on. For example, continuous one is like your exploration, trekking or anything, there you are exploring and you are continuously doing it. Whereas the other cases like in the chess, if I move here, if I move here, if I move here, something like episodic, there is an end. Okay, so or some other cases also, again I'm actually thinking out loud here, which never ends. Okay, yeah, definitely this is a good example, trading in cryptocurrency. Okay, machine learning, of course, that is what Google is doing. These are all like a continuous episodes, and there are some kind of episodes those are actually having the termination. So now, if you are actually getting into this continuous one, the set of algorithms that you apply here are model free, trial and error. Okay. Whereas if you know that this is a kind of a termination, then you can actually do model free also, model based also you can use. Now, in these cases, what we do here is that we apply the dynamic programming. As we know, the dynamic programming, the basic concept, which is something like divide them into the subtasks and subs problems, and then you solve it. Okay, that is what the main one I was actually talking about, MDPs and all these things, evaluate the policies. These are all the things. All right. So I'm just looking at the thing. I will just give a pause here. I want to know any questions do you have, and accordingly, we can go into the details of it or anything, please. Yeah. Do you have any questions, please? Are you guys there? Some people actually asking questions also. Let me see here. Yes, it makes a map of the house. Okay, can we say reinforcement only mainly work in model free? No, not necessarily. We can say only in the model free. Uh, it works in the model based also. The model based one should be having finite states. Okay, most of the cases that we get and try to people solve, like Elon Musk and such kind of big people want to solve model free kind of problems. For us, it's always better to start with model based, which is well defined ones. Okay. Any questions? Should I go to the next one, please? Yeah. So model free ones, okay. Here in model free, we just, as I mentioned, we always just a trial and error. We always interact with the world because we don't know the model of it. Model of it means you don't know the model of the how the world works, how the robot works, how the factory works, and everything. You don't have to model that one. Okay. So we actually learn all those things directly from the interacting with the environment. Like we are learning a bike or on the road or driving a car. Okay. These are all like you interact with the system, and then you build that particular value function in that, so that you build your network internally. So here there are two approaches. Okay. Monte Carlo approaches, MC approaches, and TD approach. MC approach is the one, what it does is that in MC approach, the episodes that we actually mentioned, right? In that one, it will always have to be actually having a termination. That is not something it is going for a long one. Monte Carlo methods, right? You actually test when we were actually conducting the Monte Carlo simulation for the banks, it does not require any physical simulation. So Monte Carlo simulation, what we were doing is that we have taken some kind of a different, all the possible combinations of the states. Okay, let us say 10,000 or 100,000 customers are there. Then we sample the space and across all the states and action pairs. Okay, let us say he is paying, not paying, paying, not paying, all these different things. Then we evaluate whether he is actually, what is the probability that he is going to default or not by March 31st. Okay, so that way, based on all his histories of the data that we are taking from the past 10 years, how exactly he is going to behave. But there, what exactly it is like, where we actually, the episodes must be terminated. Okay, so these are the things. Monte Carlo methods learn directly from the episodes of experience. You define so many episodes, paying, not paying, and everything like that. Okay, and model free is the no knowledge of the MDP transitions. MDP transitions are the ones where you know the model, you calculate that a transition probability, just like in the Delhi case I explained you, that he is actually trying to predict whether it is rainy or not and everything. There we have the transition probability, right? That transition probability knowledge is not required here. Okay, and Monte Carlo learns from complete episodes, no bootstrapping. Okay, and the simplest possibility is value is equal to mean return, whatever that you are actually, in this case, what I told you, right? Whether he is actually going to pay it or not paying that particular loan is something like you will get at the end of that particular policy execution. Policy execution is nothing but that particular simulation wise, what are the policy, if he pays up or not paying everything, then you'll find out whether he pays it or not. Okay, so these are all like Monte Carlo simulations is the best method that people use. Okay, and Monte Carlo policy evaluations is the one that in the mathematical form here. Pros and cons of this. Okay, generally it has many advantages. If whenever you are actually starting with any problem statement, please try to see that if you can actually do that simulation with the Monte Carlo. That is something like means blindly you go and just apply the Monte Carlo, so that at least you will see that whether it is working, because you can terminate it wherever you want. It's not necessarily you have to keep it at long. Okay, it learns that V and Q, the value function and the Q value function. Value function, as I explained, it actually tells that whether you are the right state or not. Q value function tells that if given that you are that particular place, what is the best action that you can take is what the Q value function actually defines. Okay, so no need for full models. Okay, no need to learn all the states. This is one of the advantages, because if I actually design that robot and my complete environment, let us say the same vacuum cleaner robot that I take, then if I want to really introduce anything, then I have to take all the possible combinations of that one. Okay, but here if you're actually defining only that episode one, you can do that. Okay, but some limitations are here. Okay, definitely it is for the episodic environments. Okay, so no bootstrapping, this is already mentioned. Okay, and of course it has to wait until the episode before return is known. Okay, so now for all these limitations, the best method is that we are actually having the temporal difference method. Okay, there we actually mentioned it is something like terminating episodes. Here it can apply in the non-terminating. Okay, and it can learn at every step, and also it can learn from the incomplete sequences. So based on the problem statement, you have to define that whether it is MDP, that means you wanted to construct the model based one, model free one. If it is model free one, your episodes are actually like a terminating one or a continual one. If it is a terminating one, then use the Monte Carlo. If it is non-terminal ones, then you actually use the temporal difference. So that is how the research has been done and people are actually using it. Okay, this is actually again temporal difference learning. These are all full mathematics of it. Okay, yeah. So I'll pause here. I'll stop here also. Okay, I'm continuously talking. If you have any questions, we'll go there. Otherwise, yeah, there are so many things are there. Okay, this is what we have implemented. But yeah, I'll stop here. Any questions, anything, any discussions in the last 10 minutes, please? 10, 15 minutes we have. Yeah.
So, to begin with, just if you could brief of how you implement this Monte Carlo simulation for such episodic situations. Just an overview. I know this is not a hands-on session, but
Yeah,
if you
yeah,
could summarize.
yeah. It's very simple, madam. Monte Carlo is like you have to take all the possible combinations. I'll give you a very simple example. Let us say there are only two states are there. Okay, state. Uh, very simple toy example I can give you is that uh, should I buy this car or not? Okay, something like you want to do. Okay, now what you do here is that the two states are buy or not buy. This is the decision you want to take. Now, for this one, you actually define set of parameters. Like, let us say, how much money should I do this? How much money is required? How much money am I earning? How much is it actually costing me more to maintain it? And how much benefit? Okay, how many trips I can go with my family? Like that, you can actually take some 4 or 5 parameters. Okay, now what is that you wanted to do here? It is nothing but we all do in our brains every time, right? The same thing. What you do here is that now, whether to buy this car or not, you actually take the cost. The cost of the car here is the 10 lakhs to 18 lakhs range. Okay. Now, the cost of the car, the maintenance of the car per month is something like 8,000 to 12,000. The number of trips that I'm actually going to be covering is something like 10 trips to 15 trips. So here, if you observe from the from the from the first parameter everywhere, I define them into different brackets of it. Now, what I do here is that Monte Carlo simulation is nothing but PNC, permutation combinations. Let us say if I'm earning in 80,000 rupees per month, and the car rate is 16 lakhs, and the number of trips is 11, and if I'm actually going with the family trips like 4, then how much it is actually going to be costing. That function you have to write down, like that function you define it. Again, another path, again, another one, again, another one, another one. So you do all these simulations and everything. And as many simulations as you do, you will get it finally. Then you will actually get it like most of the times based on your measure, it will say that buy or not buy. Are you getting me, madam? So that way you actually take this particular decision like whether to do it or not to do it. And it is not necessary that it is not necessary that you have to take all the permutation combinations. You can take only two things. Let us say the episode that you define here is that, hey, forget, I don't care about cost of my car when I go for my family trips. Then you exclude that one in your complete simulation and see how it is coming. You're getting, madam? So like you
Yeah.
actually construct that one to know that how it is actually working. Okay, that's the best example I can give you. But there it has to end somewhere. But whereas in other situations, let us say I'm learning bike riding. Okay, now how many permissions combinations I can give? It is a continual learning, right? It is a continual. There is no episode there.
Mm-hmm.
Okay, there I cannot apply the Monte Carlo there. So the Monte Carlo is actually going to help you kind of a model of the system where decision, what state it is better is what it is going to help you for different episodes that you are actually going to execute. For example, many people buy the car, just buy the car. They don't go with the families. The number of families they go only for 2 times, but the amount that they are getting only 60,000 rupees per month, and the amount that they're actually maintaining insurance is more than that, then at the end of the day, its decision is not to buy, because which is something like you're not using it for your purpose. So these kinds of scenarios, you will actually get the model for your better decision making.
Okay. All right. Thank
Yeah.
you.
Yeah. So yeah, this is what all about. And just last and final, I just would like to talk about, if you allow me, guys, our company is our company is Aizen. Okay, we are located in both Hyderabad and Bangalore. Okay, and currently we are also solving some interesting problems using computer vision. Okay, we are building these AI agents, and now when I'm actually building some of these different agents and everything, I'm using reinforcement learning framework, but not for all the problems, only for defined set of problems only. Especially we keep these cameras in different working environments, and see how that particular behaviors of I think the traffic, manufacturing the food, whether it is actually going it or not, the pose estimations, and also the different behaviors of the people in social environments. So we implemented this particular video AI platform, and also we have deployed it. We have deployed it in Vantara. How many of you know Vantara? So this Vantara is the place where we have actually deployed in capturing the animals' behavior through cameras. We are actually also working on some interesting projects uh, related to the multimodality, where especially the communication among the elephants. Okay, we have actually collected lots of data. These are all the elephants actually going out for walk. So we have collected the data of the elephants, and we collected data from voice, video, and there is a person who is actually telling about their behaviors. So with all these things, the different sensors data, that is we are actually getting different multimodality data, and we are able to build the communication among the bears and everything, bears as well as elephants and birds, crocodiles and cheetahs. So this is one of the interesting projects right now we are all working on. So I'll stop here. Any other feedback, questions, please let me know. Sorry, I'm continuously talking. So I want to also have some water here. Any other things, please? All right, I think good. Thank you so much. Oh, there are some
Uh,
from the people. Is there a
if,
possible?
if there's nothing, sir, we would like to wrap up the session. Thank you so much for such an interactive and detailed session.
Yeah,
We really appreciate your approach. Sir, I would also request you to kindly share the slides so that participants can refer to them.
sure, sure. I'll send it.
So I think before the anchor wrapped up, actually, I just thought maybe I can write to you. Is it possible to write to you?
Yeah. I gave my email ID already. Otherwise, I'll paste it in this group. Please feel free to contact me. Or WhatsApp is better. I generally easy to communicate.
Yeah.
Okay, I just put my number and my email ID there. Okay, please note it down. And if you want, I can share
Thank
my.
you, sir. It was a good session.
Yeah. Thank you. Thank you so much.
Yeah, sir. I just wanted to discuss further, like if there is a possibility to do some qualitative work in this area. So I can write to you, right?
Yes, absolutely. In fact, right now I'm looking for a good set of people to work on some of the projects that I'm working on. However, these are all like pure AI problems, which requires a lot of dedication and commitment. Problem here is that what I had seen in the market, if it is okay if I take few minutes, guys, otherwise let me know if the serious time constraint is there. Okay. Now, based on my experience, what I had seen in the market right now, I think many of you are students. That's why I'm trying to give you this feedback. And people expectations are so high when I go and tell AI. They think that we have to do the magic. They think that we have to do some magic and give them the results. Also, the hype around from these media channels, also the expectations of the people also high, which is actually having advantages and disadvantages. That is what I mean. Advantage here is that for many people who are picking up this AI, they're landing up very good high paid jobs, which is very good. And the disadvantage is that when these people are not able to show that results, they're getting fired also. I'm talking the outside scenarios, okay, which is very, very. But what is the solution for this? For you people, the best tip I can give you, which is working out for me, is that understand the problem statement clearly from the client. Okay. Tell them upfront what are your expectations. And even if it is your manager, whoever it might be, ask them their expectations. If those expectations, you are the person, build that AI knowledge to validate whether it is practically possible or not. If you are able to validate practically possible or not, then that is your best bet. Otherwise, what happens here is that I had seen many organizations there, they're expecting this model has to be built, this has to be done, that has to be done, this has to be done. But that would never happen. They are actually telling that I think these people are not doing anything. It is not their mistake, not at all. But it is our responsibility as we are in this AI, trying to become like a future AI experts. It is our responsibility to really go and educate the people who are non-AI people, educate them and tell them that what is feasible, what is not feasible. And this is what I wanted to give you a good feedback, because most of the students who come here also, I observe in our organization, they always say that, sir, ye ho jayega, wo ho jayega. But no, that's not the true reality. The actual AI we would accomplish maybe after 200 years. Whatever we see AI is a hyped AI. The true AI is what, if you understand that, I think all of you are great success. You will see the great success, my friends. Okay. And don't get into the prey of these people say that if I do this course, people go and pay like 5 lakhs, 10 lakhs to these some. I'm not demotivating those institutes. I mean, it's private institutes, I'm telling. If you want to really learn the AI, you are at the right junction right now where you are attending it, where all the professors who had thought about the problem and you learn much better from them. Then some people call it as AI, but not the AI. Sorry, I'm a bit judgmental here. It's not that
No,
there.
no, thank you, sir, for
I'm
very
just.
useful comments. Actually, in the chat, I have posted one LinkedIn.
Uh-huh.
Uh, yeah, this is an impact collaborative, and
Oh,
we would like you to discuss this further, maybe with
yeah,
you.
yeah, yeah, definitely. Absolutely. Absolutely. I'm
This
very,
is creating responsible pathways for AI. So
yeah,
this was started by my friend and some others.
absolutely. Absolutely. That's what, if we can focus on the actual AI problems, I think our success is also practical and accomplishable. That's what my message to all of you guys. Okay. Thank you. Thank you so much for all listening. I'm available on this email ID and phone number. I generally prefer the WhatsApp messages, and I'll be in touch. Anything, I'm happy to help. Okay. Thank you. Thank you very much. Have a great day. Bye bye.
Thank you, sir.